Hey folks, and welcome back to the video lectures for Philosophy 120, Critical Thinking. So what we're looking at today is a continuation of the never-ending discussion about arguments and how to analyze them and how to tell when we've got good ones. So what we're focusing on in particular is what's called categorical logic. You're going to hear that term categorical quite a bit over the next couple of lectures. And I'll guarantee we'll explain what it means and how all this stuff fits together. But for now, as we plan ahead and look ahead, so what we're going to do is glance at some big picture stuff, go over what it means to deal with categorical statements and concepts. We're going to glance at some of the philosophical background to this sort of thing, and then go into the basics and rules of how this kind of stuff works. Essentially, we're digging into the first of our several different systems of logic or systems of arguments that we use to analyze and present ideas. So let's go ahead and get to it, shall we? So far in the semester, we've looked at the different conditions for cogent arguments, what our textbook refers to as the ARG conditions, where we look at the acceptability of premises, the relevance of those premises to the conclusion, and how well those premises ground the acceptance of that conclusion. Now, so far, our past units have looked at the A and R conditions. And so our job is to start looking at some of the different ways that arguments can satisfy that G condition. In other words, we're looking at different sorts of ways that the premises can rationally ground the truth of the conclusion. If we look at the premises on their own, how well does that evidence sort of ground a rational acceptance of the conclusion? How well do those premises link to and sort of determine that that conclusion is true? Acceptability determines how well we can we trust these as being acceptable, plausible statements? Is there good evidence for them? Are they true? Relevance talks about how those things link to the conclusion and whether or not we can move from that evidence to the conclusion. Whereas the grounding is all about how well it justifies the conclusion. It's one thing to establish the relevance of a premise. It's another one to say that not only is it relevant, but this is enough to say that the conclusion is true, or that we've got good reason to accept the conclusion. Now, for now, we're only going to be focusing on different forms of deductive logic. If you remember from way back in the semester, we talked about some of the things like the difference between deduction and induction, and we'll look at some of that. But for now, we're specifically focusing on deductive logic, where, just as a reminder, a good argument, a cogent argument, is one that the premises, if they're true, must guarantee the truth of the conclusion. It's what we might call truth-preserving reasoning. So long as the premises are true, we'll get true conclusions out of it. Now, this also means that because we're dealing with the category of deductive arguments, that we're also dealing with what we'll call valid and sound arguments. A cogent argument, by definition, is a sound argument. It's a valid one that guarantees the truth of its conclusions and has true premises. And so all we care about for validity, all we care about for establishing that kind of thing, is looking at the structure of the argument and how well the general pattern and form of the kinds of premises and inferences we're looking at link to that conclusion. And this is all stuff that we'll get to a little bit later. This is meant to be the bring the words back to your brain segment of the lecture. So if you're not remembering the details of this or you don't see how it's relevant just yet, it's all right, bear with me. Now, it's also worth saying, just so we have a little bit more big picture context for this whole thing, that deductively valid arguments always satisfy the R and G conditions, at which point that if you have a valid argument, you know that the R and G conditions for a cogent argument are satisfied, and all you have to do then is evaluate how acceptable are these premises. Is this a sound argument in addition to being valid? So, food for thought, as well as being, like I said, sort of the big picture look at this sort of thing. So, if we're looking at different ways we can satisfy that G condition, if we're looking at different ways that the premises can ground the acceptance of that conclusion, one of the different systems used to establish a good link between premises and conclusion is the system of logic called categorical logic. And this is the sort of thing that we're going to be focusing on for this unit, so this lecture and the next. Now, categorical logic has to do with logical relationships between categories and groups of things. So it's not just about any old logical relations ever. This is not the one and only system of logic. Rather, categorical logic has to do with the relationships between kinds of things. It's the kind of logic that deals with stuff like some, all, no, are, and not as the basic logical terms and operators. So categorical logic has to deal with how different groups of things or concepts fit together, where you say things like all men are mortal, or all immigrants are bad people, or all Toyotas are reliable cars, or things like this. And it's not just these broad general statements. We can also say things about smaller groups of things. We might talk about how all men are mortal implies that some men are mortal. We might say that the fact that some immigrants are criminals doesn't mean that all immigrants are criminals, and so on and so forth. There are different relationships between groups of things, and these relationships matter quite a lot, especially when we deal with the kinds of examples I was just pulling from, things in economics, things in politics, things in every aspect of our lives. So categorical logic sounds awfully specific at first, but it's a very broadly useful system of logic. It's something that we can use to talk about a lot of different topics. Now, valid argument in this system is all about the deductive relationships between the categories being discussed. When we talk about deductive relationships in either the book or the lectures, we're talking about relationships that necessarily are the case, ones that you can be sure about. There is no probable inference between these things. We're talking about relationships that are guaranteed based on the truth of the things involved. Like, for example, all men are mortal deductively implies that some men are mortal. It's just a necessary relationship between those two categories. All men includes some men. It's impossible for that first one to be true and the second one to be false, so long as some people exist somewhere. So when we're talking about deductive relationships between different categories, another example, one that again talks to different political issues. Some Americans are prisoners. All Americans are people with rights. Therefore, some prisoners are people with rights. This is something that we can infer based on those original couple of statements. So categorical logic has to do with these groups like some, all, and none, and how these different things relate to each other. What does this fact about this category tell us about other categories or other groups? Now, it's worth noting that not a whole lot of ordinary sentences are phrased like this. You probably don't hear all, some, or none in every sentence of everything you deal with. It's just not a way that we always structure sentences. So we have to do some translation. But we've started doing some of that already in this class, where I've had you look at arguments out in the wild, or your homework's had you look at various sentences and try and build a standardized argument out of them. We're going to have to do the same thing for this, where we look for ordinary natural language sentences, we might call them, or ordinary language sentences, and occasionally translate them into these categorical structures and forms. Now, just as a bit of background, it's worth noting that Aristotle is actually the first one who came up with this sort of logic. Now, this isn't a history class. I don't care that you know the dates of Aristotle or necessarily who he was. But Aristotle's a classical Greek philosopher who saw the relationships between these different sorts of terms and literally invented or discovered, depending on your view of the sort of thing, the different rules of inference that allow us to deductively infer conclusions about different statements in this form. He literally invented logic, among other things. One joke that I often tell my intro to philosophy students is he literally invented being smart. Basically, everything that people study, Aristotle established the main foundation for 1,000 years in that field. He saw himself primarily as a biologist, but his physics was used for, well, pretty much up until Newton. His work in metaphysics influenced philosophy and religion for 1,000 years. Just everything the guy did was massive, and his logic was part of that. So the main rules that we study are 2,000-year-old rules that were discovered or formulated at least by Aristotle and are still very much worth using and validating. It's not stuff that goes out of date. Now, Aristotle himself even knew that this categorical system we're about to talk about for this lecture and next can't capture all the different deductive relationships. Like when we talk about categorical logic, like we did just a moment ago, we're talking about groups like some, all, and none. And we're using sentences like all men are mortal. We're talking about one term or category, and we're talking about how it links up with another group or category. And this can't capture all the different deductive statements or all the different deductive relationships. There's no rules or structure for dealing with or statements, for example, like either he's lying or he's telling the truth. We can't deal, categorical logic doesn't have systems in place to deal with that kind of statement. It only works with things in categorical form. So it's limited in some of what it can do. But that's why we have other logical systems as well. Things like propositional logic that we're going to look at, or you might have predicate logic. There are different systems that you can create for different situations that operate on different sets of rules. Furthermore, it's also worth noting, just as a philosophical note, that Aristotle saw his system of logic, this categorical logic, as only applying to actual, real, existing things. He held what we might call the existential interpretation of categorical sentences and statements. So again, we're working with statements that are in this form, this categorical form that deals with the relationships between categories and groups of things, which means that we use terms like some, all, and none. So, like some Americans are prisoners. Aristotle held that this statement's only true, or that if it's true at all, it's because there actually are some Americans. And in the case of this instance, modern logicians would also agree. When we talk about things like all Americans are people with rights, or we say that all men are mortal, Aristotle believed that that statement being true, that all men are immortal, can only be true because there actually are men who die at the end of their lives or something like that. And this is actually quite controversial for modern logicians. Modern people who study logic often deal with a different sort of philosophical assumption in the background, what we can call the hypothetical interpretation, where categorical statements don't, on their own, imply existence. So if we go back to this example, all Americans are people with rights. Aristotle would say that this sentence, that this statement, if it's true, then that implies that there actually are such things as Americans, which overall seems safe until you start thinking about things like unicorns and dragons. If I say all dragons breathe fire, well, that sentence is either true or false, or at least it seems like it. But there are no such things as dragons. So it doesn't seem like there have to be dragons for it to be true. Or if I say all hobbits have hairy feet, or take whatever fictional, imaginary sort of creature or topic you want to talk about, it seems like we can still do logic and think rationally about these kinds of topics in ordered, structured ways, because that's all logic is a structured way of thinking that tries to get to preserve truth through its whole reasoning. It doesn't really work with the existential interpretation, or at least it doesn't do so without being very complicated. So most viewpoints now hold what we call the hypothetical interpretation. We say that if there are such things as Americans, then it's true that all Americans are people with rights. Or that if there were such things as dragons, then we can say that all dragons breathe fire. So it's not something that's going to radically change how we deal with most of this, but in a couple of specific and tricky cases, it's worth noting that this sort of philosophical assumption is going in the background. We're going to follow modern logicians and generally say that the hypothetical interpretation is the correct one to take. But Aristotle's a smart guy. It's worth at least being aware of this sort of thing, especially since it's some of the foundational thought about this whole subject. So, let's actually start getting into how categorical logic works, shall we? So, categorical logic, like I said, is the logic of dealing with the relationships between categories of things. And that means if we follow Aristotle's system, which we are, categorical logic then is based around the relationships between four basic kinds of statements. And these kinds of statements are labeled with letters, following the traditional structure of things that are based in Latin names that I do not want you to know. And these are the A, E, I, and O statements. These different sentences use all, some, or no to describe things, and they usually are linked, or in our case, they are definitively linked with a form of to be in the middle. So we say things like all men are mortal, or all dogs are mammals, or some cats are assholes, or something like that. We're talking about how different categories relate to each other. And so the four different statements are different combinations of these terms, and they express both universal and particular sorts of statements. So, and we'll go through all these in order. So don't worry about the details just yet. But keep in mind there are four basic sorts of statements, and each one says different things about their topics. So, A statements are what we can call universal affirmations. So these are universal statements. They use all or none. They say things about every member of the categories they're talking about. And these are positive statements. Not positive in the sense of happy, but positive in the sense they say something has some particular quality. Or more specifically, they say that things in one category are in some other category. So the basic structure of an A statement is all X are Y. Everything in category X is also in category Y. All dogs are mammals. All Americans are male. All fish breathe fire. All clouds are made of water. They don't have to be true statements, but any statement that takes this structure, because remember, structure is the only thing we care about for valid arguments. Any statement that takes this structure is an A statement for what we're worried about. It is a universal affirmation. It talks about every single member of category X. Or to add a new vocab term to all of this, that first term, the subject term in this sentence, is what we call a distributed term. The things that we're saying about X are distributed across the entire category. And this is something that we will rely on quite a bit when we get to the second half of this unit, so it's worth taking note of this. A statements distribute that first term, the X, in our formula here. It does not talk about every member of Y. So like if we say all dogs are mammals, we're saying something about every single dog in existence. We're not necessarily talking about all mammals, though. It can be true that all dogs are mammals, and it not be true that all mammals are dogs. We're not saying something about all Ys in this sentence, which, when we look at it like this, seems pretty obvious. But it's worth keeping in mind because it will matter later. Now, when we deal with these universal affirmations, when we deal with A statements, it's worth watching out for stereotypes and mistranslations when we go from ordinary language to the structured formal language of doing this kind of stuff. So make sure to not what's the best way to put it? Not to too eagerly translate things into this structure. Be careful that you don't end up saying overly broad things and stereotyping different groups where maybe a more particular statement might be appropriate. Now, another type of statement is the opposite. in a sense, of the A statement. And this is the E, the universal negative statement. So it's also a universal statement. It talks about every member of a particular category, only in this case, it's a negative statement. It's saying that members of one category are not members of another category. So the universal negative, the E statement, says that no X are Y. No things in category X are also in category Y. So it actually distributes things about category Y, and this actually got left off the slide, but it also distributes, that is, it also talks about every member in X, because it's essentially saying these two groups, X and Y, do not overlap at all. And so it's a statement about about every member of each of those groups. And it usually looks something like no failing students are students who did their homework. No dogs are creatures that breathe fire. Um, no computers are error proof devices, or whatever other things you might want to say. And remember, these can be true statements, they can be false statements, stuff we evaluate later. So, E statements, universal negatives, talk about every member of both of the categories. It is worth mentioning that when we translate these things, when we go from ordinary language to the standardized format of actually like numbering out our premises and building good syllogisms and all that good stuff, that we ought to watch out for sentences that have not all in the original versions. Like if I said, not all soccer players are good actors. Well, when I say not all soccer players, I could be talking about their no soccer players are good actors. But that's not quite the same thing, is it? In the original version, if I say not all soccer players are good actors, I'm not really saying that no soccer players are good actors. There could be one. There could be a particular player who's really good at faking getting hurt or something like that. So just the fact that in ordinary language something says not all X, that doesn't mean you should automatically translate it as an E statement. You shouldn't automatically go for that universal negative. It might also fit into some version of an A statement. If I say that not all soccer players are good actors, there are other ways of translating that sentence. We might say something more like, some soccer players are not good actors. Or we might say that some are good actors and simply imply that some are not. So there are different ways of translating it. I guess my main point here is just to warn you not to over eagerly translate things that have this not all into the universal negative. It's sometimes not really warranted. Now, third type, we start getting into the particular types of statements. This is the I type. There is a particular affirmative and a particular negative, just like with the universal ones. So the I statement, the particular affirmative, says that some X are Y. Some things in category X are also in category Y. Some children are sociopaths. Some students are good students. Some books are worth reading. These are different particular statements that don't talk about every member of a category. It doesn't talk about all of either category in this case. Neither of the terms in an I statement are distributed, which again is something that's going to turn out to be very important later. Instead, the particular affirmative only talks about part of those categories, some subset of X. Another way of reading the some X or Y is if we read it as at least one X is Y. When I say some children are sociopaths, really what I'm saying is at least one child is a sociopath somewhere. Or we might say at least one child is also a sociopath. And you can see why this starts to be one of the exceptions to that hypothetical interpretation we talked about a few minutes ago. This is one of the instances where both Aristotle and modern logicians agree that if this is true, if anything in an I statement is true, it does imply existence. It does imply that X actually exists. In other words, it can only be true that at least one child is a sociopath if there's actually a child somewhere in the world who is a sociopath. Which, if most of you spend much time around kids, I guess you can say for certain that there actually is at least one somewhere, part of the time. Children are wonderful and beautiful and fantastic in so many ways, and also incredibly cruel at times. Well, anyway, it's late night here, so I'm rambling a bit. But I statements do imply existence. Similarly, O statements, the particular negative, does something fairly similar. In this case, O statements deal with the idea that some X are not Y. Some things in category X are not in category Y. Some moral mistakes are not intentional mistakes. Some airplane pilots are people who are not good at their job, or they are not people who are good at their job. We might also say some dogs are not mammals. Again, we can have false statements fall in these categories. So that the particular negative statement, in particular, it excludes one category from another. It excludes at least some part of category X from category Y. So we might also rephrase this as not all X or Y. We might say at least one X is not Y. And so, just like the I statement, the O statements do not imply existence. Excuse me, they do imply existence. It's late and I don't know what I'm saying. But O statements, particular negatives, they do imply existence. They are one of the few exceptions to that hypothetical interpretation we talked about before. And it's also worth noting and rephrasing again, because it's going to matter later. I statements, the particular affirmative, and the O, the particular negative, do not distribute either of their terms. Again, this will come up later. So, those are the four basic statements. And all of categorical logic, then, is built around how those four kinds of statements, how those four structures of ideas relate to each other. And one of the traditional ways of mapping out this whole thing is what's called the square of opposition. This is a very old sort of picture with some very old vocabulary terms on it that goes all the way back to Aristotle. And essentially, this is a visual map of how the different statements relate to each other. And we'll go over what each of these different terms mean. I guarantee it's not nearly as complicated as it looks like. But the basic idea is that if I have one of these statements, there are certain rules I can follow. There are certain things that I can know automatically about other statements if I can show one of these to be true or false. And that's kind of what all of logic is. It's putting those different relationships together so that we can actually and rationally know things about the world. So first, let's talk about some of this vocab, and we'll bounce back and forth to the square and some of the other rules to actually dig into this stuff in greater detail. So first off, one of the things that shouldn't be all that surprising, one of the main things to look at here is what's called a contradictory relationship. One statement is a contradictory of another one when it must have, these two statements, they must have opposite truth values. So A statements and O statements are contradictories according to this map. And it seems pretty obvious why. If we say that every dog is a mammal or all dogs are mammals, well, it seems like it's impossible for it to be true for some dogs to not be mammals. That is, both of these statements, if we fill in the same term for S and P, They both can't be true at the same time. In fact, they have to have opposite truth values. If I say all Republicans are bad presidents, then it must also be false that some Republicans are not bad presidents, and so on. Whatever things you want to plug in there. Contradictory statements must have opposite truth values. The same goes for E and I statements. E statements, no SRP, and I statements, if I can get that little bit to go away, it says some SRP. These are obviously things that can't both be true. They must have opposite values. If it's true that no dogs are fish, then it can't be true that some dogs are fish. You just can't believe both of those things and be a rational, sane person at the same time. They must have opposite truth values. Now, a different but related sort of relationship is the subcontrary. Two statements are subcontraries. They're subcontrary to each other, just like the first one might say they are contradictories, or they are contradictory to each other, or of another one. Subcontrary statements are subcontraries if both cannot be false, but they can both be true. So let's look at this for a second. Two statements are subcontraries if both cannot be false. That is, they both can't be false at the same time, but they could both be true. So let's look at the idea some people are nice, some people are not nice. These two statements are subcontraries. The book, I think, uses this example, and I think it shows up in several different places. It works out rather nicely. It cannot be false that some people are nice and also be false that some people are not nice. One of those two statements must be true. It's like saying some things are red and some things are not red. Both of those can't be false. It can't be the case that neither red nor not red exists somewhere in the universe, because it's effectively what you end up saying with that kind of thing. Rephrase this again, taking away the sum. At least one person is nice. At least one person is not nice. It can't be false for there to both of these statements can't be false. It can't be the case that there's neither one person who's nice nor one person who's not nice. But it can be the case that both of these are true. It can be the case that some people are nice and some people are not nice. This is a basic fact about the world. So subcontrary statements, they can both be true, they can't both be false. If we go back to our square, I statements and O statements are particular statements. These are subcontraries. These are things that can both be true, but they can't both be false. And so long as we're talking about the same predicates, the same categories, the same properties, then this seems kind of straightforward in some cases. Again, let's plug in a couple of other examples here. If, say, we want to talk about dogs and mammals again, let's say that some dogs are mammals, which is true. It's trivially true because all dogs are mammals. But let's say that some dogs are mammals. That can be true. And let's say, weirdly, that some dogs are not mammals. Let's say it's the kind of thing that a mad scientist has found an odd way of making a reptilian dog. I'm sure the people who keep iguanas for pets were absolutely thrilled at this point. Now, if we're dealing with dogs and mammals, it cannot be the case that some dogs are mammals and some dogs are not mammals. They can't both be false, but they could both be true. Or again, if we deal with red and not red, or something like that. Generally, the kinds of properties we're dealing with here, I wish that bar would not keep showing up every time I aim at the bottom of this thing. Every time we deal with the not P and the P side of this, we're dealing basically with the options that govern everything. It's like if you've ever seen that joke image that floats around on the internet somewhere, that you there's a somebody will put up a picture of two different books, the things they teach at Harvard Law and the things that they don't teach at Harvard Law. In theory, if both of those titles were accurate, those two books would contain all of the knowledge of the universe, because it has both things they teach at Harvard Law and the ones they don't teach at Harvard Law. Those two labels cover pretty much everything. So you can't have it be the case that there's nothing in both of those categories. So long as those labels are meaningful, they have to apply to something. And this is basically the way that subcontraries work. They both can't be false, but they could both be true. I statements and O statements are subcontraries. So, a couple of other relationships that we need to be aware of. One of which is logical equivalence. Two statements are logically equivalent if they both necessarily must have the same truth value. And some statements, this works out rather straightforwardly. Take something like no circles or squares. This is logically equivalent to no squares or circles. Now, it's worth stressing that first word there, the logical part of the equivalence, because we're not saying that these two statements say the same thing. Rather, when we talk about logical equivalence, we're only talking about the truth values. We're only talking about they must both be true or they must both be false. The negative statement we're using here, I guess, doesn't illustrate the difference between logical equivalence and actual equivalence very well. But I guarantee that if you work through enough examples, you eventually will find two statements that do say somewhat different things, at least on an ordinary sense. But logically, the truth values still have to end up being the same. Now, finding logically equivalent statements isn't something that's mapped out here on the square of opposition. Instead, this is something that we figure out through different rules of inference that we'll talk about a little bit later. But it's still a relationship that we need to know the name for. Now, another term that shows up on some pictures of the square, but not on others, I don't believe it's in the one in your book, is called subalternation. And this is when one statement implies another, but doesn't imply the truth of this statement in reverse. It's one-way implication, so to speak. So when we look at the square here on the PowerPoint slide, A statements subaltern I statements. That is, if it's true that all dogs are mammals, then it is also true that some dogs are mammals. Similarly, if it's true that no bachelors are married men, then it's also true that some bachelors are not married men. The broad universal statement implies or contains that smaller, more particular statement. And in some places, you'll see the term subalternation to describe that one-way implication, but you won't see it everywhere. Again, your textbook doesn't actually use it. But if you end up going and looking up things on the homework, or if you look in other books, or you just decide to carry on with your education in critical thinking and logic, it's worth knowing the term, I think, so that you can go back to it and at least be mildly familiar with it. Now, a few other things that aren't on the square of opposition, but are very much worth knowing about. And these are ones that your textbook does use and stress. One of these is the notion of a complementary predicate. And this is a predicate, a term or a label or a property that, when paired up with its complement, forms a pair of contradictory statements. Basically, a complementary predicate is just the logical, I guess, the logical opposite of whatever it is we're talking about. Not the actual opposite, but a logical complement. It's something that rounds out the rest of the logical picture if we're talking about everything in the world. The usual way of describing these, the usual way of writing this down, is to use the term non. Or if you end up stacking a couple of nons, you can reduce those down. And something that is not P is P. So you can cancel out two of those at a time if they ever end up stacking up on you in different instances. But the reason why I stress this, say that it's only a logical opposite, and that we use this term non, is actually a rather important point to make. Like, take the example of two complementary predicates, happy and non happy. This is different from the actual opposite of happy. Like, if we were to straight up say, well, what's the opposite of being happy? You'd probably either say sad, or if you wanted to be really technical, unhappy would be the opposite in ordinary, regularly used English. But logically, there are more options than that. Remember, a contradictory statement is one that must have the opposite truth value. Now, if I say that uh, you are, it doesn't work as well with some of these, but the point is that uh, complementary predicates are meant to exhaust all of your options. If I say that you're not happy, if I say that it's false that you're happy, that doesn't automatically mean that you're unhappy. There are other options that exist somewhere in the middle of those two terms. But happy and non happy, there is no middle ground between those two. This is very much a binary choice. You either are happy or you are non happy. That's not to say that you're sad, it's not to say you're upset, but maybe you're just kind of mellow. You're non happy. That is, you're not in some state of happiness, but it doesn't automatically mean that you're unhappy in some sense. I think other predicates, this is even easier to see things with. Take red and not red, or non red. These two are complementary predicates. If we pair these together, we can make contradictory statements. It's the statement that something is red and something is not red. These two are contradictory statements. They must have opposite truth values. But that's not the case if we try and come up with some other predicate. If we said red and blue, if we wanted to go with some generic sort of opposite. Well, that doesn't exhaust all of our options. We're not dealing with actual contradictory statements here. So when we talk about complementary predicates, use something like the term non, and remember, the two complements are meant to exhaust all of the logical options. That's not all of the reasonable options, but all of the options available, period, when we're doing logic and thinking about these kinds of things. Um, Another thing to note, contrary predicates. Excuse me. Contrary predicates are two predicates that cannot both at the same time cannot have or be in one thing at the same time, but it is possible for something to have neither of them. So just like contraries or subcontraries are things where we're dealing with different combinations of truth values, contrary predicates have to do with properties that can be in an object at the same time, or that can't be in an object at the same time, but it could have neither. If we go back to our happy and unhappy example, happy and unhappy are contrary predicates rather than complementary. A thing can be neither happy nor unhappy, but it can't be both happy and unhappy, at least not in the same way, the same place, and the same time on the same object. Um, so contraries are things that you can't have both of. They can't both be true, but it is possible that they're both false or that a thing has neither of the two properties. Now, here's why we have labels for each of these. I know that this is feeling probably a little bit confusing, a little bit repetitive, and all that, but there are often instances when we deal with false dichotomies in arguments or in reasoning or in just general life and communication. And you've probably heard of a false dichotomy or a false binary or something like that. And this is when we have a fake choice between two extremes. Um, like, again, I hate going back to politics, but it shows up in the news so much. And so while I'm officially neutral on all topics, we can still draw some examples from it. Take something like simple voting, which you should do in the upcoming midterm election, regardless of who you uh, agree with or whatever else. It's a good thing as a citizen to vote. Anyway, getting off the soapbox. People will often say you only really have two choices when you vote. You can vote for the red team and you can vote for the blue team. But that's not actually the case. There are actually other options. There are independents, there are third parties, and so on. You have more than just the two options. Or if people say, well, if you don't go to college, well, then you can be homeless and live under a bridge at some point. These are not your only two options. And these sorts of false dichotomies, this fallacious assuming that there are only two options that exist on a given topic, that whole mistake lies in failing to distinguish between these two sorts of things. Some things are contrary to each other, but they're not complementary to each other. That is, they don't form the full range of options. Take, like, say, voting Democrat or Republican. You can't vote both Democrat and Republican for the same person, for the same office, and so on. You can mix your total ticket, but you can't vote for both a Democrat and a Republican for the same job. If you're voting, say, for mayor or something like that, only one person gets elected. You can't pick both. You can pick neither, however. There are other options in the middle. Similarly, if we're voting for, or if you're trying to distinguish between Republican and not Republican, those two options are exhaustive. They do list all of the different possibilities there. So these two things are complementary predicates instead. So the distinction between these two is worth noting. False dichotomies and confusion about options happen when these two things get mixed up. And this matters, especially when we start dealing with this kind of nonsense, because if we're not careful, we'll end up making mistakes and coming up with nonsense if we confuse these kinds of things. So it's worth taking the time to really think about what these definitions mean and to make sure you go through enough examples out of the textbook or in homework or even just thinking about it on your own to make sure that you can keep some level of distinction between them in your own head. Excuse me. So, last bit for this lecture then. So, what we've looked at so far, I know it's been a lot of vocab and it's a lot. When we start talking about truth values and things that must have this, they can't both be this, it's easy to get your head sort of buried in all of this. Or if you're following along with it rather well, a lot of it might look obvious. Awesome. So we're going to throw a little bit more vocab at what we're doing, or throw a little bit more vocab at you. But it's where we start to actually do things with some of these. So what we've done so far is we've looked at the basics of categorical logic and what it is. It's relationships between categories of things, or the concepts of categories of things. Categorical logic is built around four different basic statements: A, E, I, and O statements. These statements have a few basic relationships to each other. Some of them are contradictories, and they have to have opposite truth values. They can't both be true. In fact, if one's true, the other has to be false. Others are subcontraries. They can't both be false, but they can both be true. And then others imply others, and others are contrary statements. Now, out of these basic relationships, and with this vocabulary, we can actually start learning things about the world. We can use one statement to immediately infer other statements and know for a fact that they're true or false. And these use what are called the rules of immediate inference. That is, these are rules or logical operations that allow us to infer one statement from another without any steps in the middle. We don't have to form big, long arguments. These are places where we get to skip making big, long arguments. Instead, these are ways to validly infer one categorical statement from another. Or if you want to think about it, there are ways to turn one statement into another, depending on what we're talking about. So, there are 4 basic rules of inference we're going to work with that, I guess by coincidence, match up with the 4, but they're not particularly tied to any of the 4 statements before. But the first and the simplest of these different rules of inference is what's called conversion. This is the process where all we do is we simply flip around the statement that we're talking about. So all x or y becomes all y or x. No x or y, no y or x. Some x or y, some y or x, and so on. We just literally take the 2 terms and we rotate them, we flip them. Now, why on earth would we want to do this? Well, for one, it's a step used in a couple of the other operations. But 2, for E statements and I statements, the converse is actually logically equivalent to the original. So depending on the kind of statement we're working with, we can actually, just by flipping the terms around, automatically infer another true or false statement, depending on what we're working with. For example, if we say that some x are y, that's logically equivalent to the statement that some y are x. Logically, it just follows. It's just true that if some dogs are puppies, or excuse me, if some puppies are dogs, then some dogs are puppies. If some red things are also blue things, well, then that automatically implies that some blue things are also red things. On its own, that doesn't sound particularly informative, but depending on what categories you're working with, that can actually be quite interesting and worth knowing. And similarly, this works for the negative version of this as well. If we're talking about some x are not y, well, then it's also the case that some y are not x, and so forth. Now, it's worth noting that conversion does not work on A and O statements if we're looking for logically equivalent ones. You can convert A and O statements. You can flop around the terms just like you do everywhere else. I did these first 2 examples right here. But these 2 statements are not logically equivalent. So A and O statements, this will not produce a logical equivalent. The fact that all squares are rectangles is not equivalent to the statement that all rectangles are squares. The first one's true. All squares are rectangles by definition. But it is not the case that all rectangles are squares. Some rectangles do not fit that definition of square. So even though I can do the operation, I can flip around the terms, it doesn't give me a logically equivalent statement. And the same is true for the negative ones. Yeah, so I won't bore you with all the details on that. But let's go on with the other rules of inference then. So contraposition. This is the first of our more complex one. This is the same as conversion, where we are flipping around the different terms that we're working with. But we also add a non onto each category. So effectively, we create complementary predicates for each of the things that we're working with. So, for example, if we're working with the statement no x are y, which is an E statement, it's one of the universal negatives. To form the contrapositive, it's called, of this statement, if we're going to perform contraposition, we flip the two terms around. So we have y and x in a different order now, and we slap a non onto each one of those. So no x are y becomes no non y are non x. Similarly, if we want to work with the particular affirmative, some A or B becomes some non B are non A. All X are Y, and so on. That one's actually a mistake. That should be an all in both places. But contraposition. These, again, in some cases produce logical equivalents, in some cases they don't. The A and O statements are logically equivalent to each other. If we write out all squares are rectangles, if we do the contrapositive of it, all non-rectangles are non-squares. And this honestly seems rather straightforward if we take it slowly and look at it. All squares are all squares are rectangles. Okay, that's true. By definition, if a thing's a square, it has all the properties needed to be a rectangle, so that's true. This first statement has a truth value to it. Now, if we do contraposition to it, we flip it around and form the complementary predicates. We slap a non on each one. All non-rectangles are non-squares. Well, that ends up being true, just like in the first case. If something's not a rectangle, it can't be a square. If it's got only three sides, it can't be a square. If it has hair, it can't be a square, and so on and so forth. Now, E and I statements do not form logical equivalents when we perform contraposition on them. For example, if we use the universal negative here, the E statement, no women are actors, that's not equivalent to no non actors are non women. So, no women are actors. Okay, let's take that as true in the most technical of senses. We're using actor and actress in a very strict sense. No women are actors. Okay, let's say it's true. No non actors are non women. So there are no non actors that are not women. That is, women have to do every other non acting job. Well, that's obviously not true. So here we have a true statement and a false statement. These two are not logically equivalent. Remember, logically equivalent statements have to have the same truth value necessarily. They literally cannot have separate values. So, contraposition, flip around the terms, slap nons on it, produces logical equivalents for A and O. Obversion. This is another one of our two-step rules of inference here. So first, excuse me, gotta keep clearing my throat for some reason. So, obversion. Two steps. First, add a non to the predicate category to form a complementary predicate. That is, put a non on the second term in the statement. If we're using the grammatical terms subject and predicate to label the first and the second parts of the sentence, you add a non to that second category. Then, change the statement from a positive to negative or vice versa. This will produce a logical equivalent in every single instance. No matter which of the four types of statement you're working with, obversion will create a logical equivalent. So, for an example here, Let's say all men are cowards, which is a false statement overall. There are at least some, rather brave people out there. So, all men are cowards. First step, we put a non on the second term, the predicate term, the predicate category. So we go from all men are cowards to all men are non-cowards. Then this is a positive statement. This is a universal affirmative. So let's make it the universal negative. So we go from all men are cowards, all men are non-cowards, to no men are non-cowards. And this and the first statement are logically equivalent. If it is false that all men are cowards, it must also be false that no men are non cowards. Because if it's false that all men are cowards, that means that there's some dude somewhere who's brave. And this says no men are non cowards. There are no people, no men who are non cowards of some sort or another. Well, that's also false. If this one's false, that one's false, and vice versa. These two statements are logically equivalent. And this will work for any example we want to throw on it. If we want to say that all dogs are mammals, all dogs are mammals, all dogs are non mammals, no dogs are non mammals. And that seems true. We know that it's the case that all dogs are mammals. We also know that's the case that there are no dogs that are non mammals. There are no reptilian dogs. There are no bird dogs in a literal or biological sense, and so on and so forth. So, no matter what kind of statement we plug into this, obversion will create a logical equivalent for us. It's an operation that works on all four types. Now, the last of our rules of immediate inference is contradiction. And this is worth a little bit of special mention. This is not a way to infer a logically equivalent statement. So, whereas the rest of these have at least one situation that produces a logical equivalent, contradiction does not. In fact, it's by definition a way to refute a statement. Remember, contradictory statements are ones that cannot have the same truth value. So if we go back to that square of opposition, these are the ones that were on the opposite corners and go diagonal to each other. A statements and O statements, and E statements and I statements are contradictories. So if one's true, the other must be false, and vice versa. And on its own, that maybe seems obvious, but there are some instances where we can use that relationship to still immediately infer another statement and to determine that it's true or false accordingly. So if we're looking for counterexamples, this is a fantastic relationship to keep in mind. For example, take the statement, all women are people who suck at math. This statement and its opposite on the square, some women are not people who suck at math. These two things are contradictories. If it's true that all women are people who suck at math, well, then there can't be any women who don't suck at it, and vice versa. If there is at least one woman somewhere who does not suck at math, who, thank God, exists, then it's false that all women are people that suck at math. If we can show that one of those two statements is true, the other one must be false. So in order to disprove the first statement, all we have to do is establish the truth of the other. And in some situations, this is a very valuable relationship to keep in mind. If trying, say, to disprove that universal affirmative statement, all you have to do is prove the particular negative statement. Some women are not, or some women are not people who suck at math, and so on. So this sort of relationship opens up new strategies for dealing with arguments and refuting positions or establishing new ones. So even though it doesn't give us logically equivalent statements the way that the others do, we can't use it to produce new statements. it is still a valuable sort of thing to keep in a toolbox when we're doing all this categorical logic stuff. And that about wraps it up. I know that it's a lot of vocab. I know that it's a lot of small, finicky details to keep in mind. But if you look through the first part of the homework, you should be able to cement some of these things down a little bit more, get a little bit more practice at translating sentences into these structures, labeling the different kinds of forms. Because once we have that down, next time we're going to start using these basics to actually start building full arguments and analyzing those arguments as part of categorical logic. So once you've got a handle on some of the vocab here, take a look at the first part of the homework, get the practice in, get familiar with some of the terms, and then go ahead and tackle that next lesson. Don't forget to keep an eye on the most recent due dates for the section, which are posted with that unit checklist and on all of the assignments. And yeah, good luck with the first part of the homework. Take a look at the journal if you haven't already and see how you feel about it. And happy thinking, guys.